This is the solution to problem 427 of Halliday, Resnick, and Walker. Let's go look at the problem. This problem says we've got an airplane that is diving at a certain angle below the horizontal here, and then it's going to release this decoy, and the decoy is going to experience projectile motion as it heads down here. And we know that the distance that it travels, that distance d, is 700 meters. So then questions, how long is it in the air, and how high above was that thing released? The first thing I want to talk about is certainly 290 kilometers an hour is pretty fast, and it's clear that if something's traveling that fast that we can't really ignore air resistance. And I'm a little surprised they didn't put a statement here in the problem that said, ignore air resistance. So I am going to go ahead and sort of stick that in there explicitly. Really, it's probably not a completely realistic problem. I hope you weren't thinking that you had to do something with air resistance, because you don't really know how to work with that at this point. All right, well, of course, the next thing to do, as always, is to set up a coordinate system. And here I decided to set up a coordinate system with my origin up here at the place of release. And so there's my x-coordinate off to the right, and then the y-coordinate is I'm having positive be downwards. So remember, there's flexibility in how you set these up, but that seemed to me to make the most sense. So I did that. Notice one other thing here, that the plane is sort of coming down, and it looks like it's kind of curving upwards like that. Don't think that somehow impacts what's going on with with this decoy. As soon as the decoy is released, it's just moving at whatever initial velocity it had, and it's experiencing the force of gravity, which is causing an acceleration. So you don't need to think that the plane arcing up like that is going to have some sort of effect. All right, so how are we going to then proceed? We know the initial velocity is v0, so I've drawn it in there. And we know then that we're going to have to work with components in both the x and the y direction, as we always do. But first, we certainly can't be using 290 kilometers an hour. We have to do a conversion of that. So just write down that v0 is 290 kilometers an hour. And then remember how this works. We basically just want to multiply this 290 kilometers per hour by 1. So you multiply it first by 1,000 meters is equal to 1 kilometer, so therefore that's 1. And then again, multiply it by 1 hour up there in the numerator is equal to 3,600 seconds. And you can see that the advantage, or what this accomplishes, is the 1 hour, or the hour, cancels out the hours, and the kilometers cancels out the kilometers. And so what we end up with, work out the number, is 80.6 meters per second. So we've now made the conversion over standard MKS units. All right, then we need the x and the y components of the velocity. I can sort of draw in that picture here, the x velocity and the y velocity. And I think it's pretty clear that the x component is going to be the v0 times the cosine of theta. We can put in the various numbers there and calculate that, and that comes out to be 69.8 meters per second for the x velocity. And similarly then, my vectors disappeared, but if I draw those in again, the y component is the opposite side, and so that's the sine of theta that comes into play for the y component. I can put numbers in and calculate that. And notice I explicitly included a plus sign here because I want to remember that our positive y is downwards, and so that v0 is heading in the same direction as the positive y, and so that comes in as a positive number for the initial y velocity. All right, well, now the next thing to do is to go ahead and see if we can solve the problem. What we need to do is think about what the equations are that correspond to this motion. And so in the x direction, we know it's all relatively simple. The x is a function of time. Is just given by v is equal to d is equal to v times t, basically, just velocity times time, because the acceleration in the x direction is equal to 0. I can kind of make that explicit by saying, well, x of t, or v of t, is equal to just that constant v0x. In the y direction, there is the standard equation for accelerated motion there with the initial y velocity and the acceleration. And similarly for the velocity, is equal to a times t because there is acceleration going on there. I'm going to make a subtle change here. If you watch carefully, you will see that my a sub y just turned into an a sub g, and it did so with a positive sign here, and there's a positive sign there as well, because again, the positive direction of y is down, and so the acceleration we're going to do is a positive 9.8 meters per second squared. Everything is sort of going in that positive direction the way we've set stuff up. Okay, now, how are we going to solve the problem? Well, the question, how long is the decoy in the air? We can work that out because we know the distance d that this thing travels, and we know its velocity in the x direction. So it's just a distance is equal to v times t kind of a problem. I call that t final. That's the time at which the decoy hits the ground. So we just need to take that and solve it for for t, and then plug the numbers in to come up with the 700 meters divided by 69.8. That's 10.02 seconds. You can certainly round that off just to 10.0 if you want seconds for the time in this case. Okay, now with that, that's the answer then to part A. How long is it in the air? Now the question is, how high was this thing when it was released? And so there we have to go to the y equations, or the equations involving the vertical component. And if we take that y of t, basically the height, h, I'll draw that little h there, is the position of the decoy when it gets to the at that t final. So it's how far it's gone in the vertical direction at after 10 seconds. So basically we then just need to take our value of 10 seconds and put it into that equation. So I'll write it out explicitly in terms of the symbols there, and then plug in the various numbers, and then work out the number, and it comes out to be 893 meters. So basically we've got the answer to our problem here. 893 is how high was the release point, and how long in the air was 10.0 seconds. So I want to do one other thing, though. I want to think, so what, there are choices for coordinate systems, and I know some people really like to have the coordinate system origin be at the ground and have the positive direction acting upwards. So let's go ahead and do that. We'll flip that y-axis upwards, and then I'll move the y label up there where it belongs, and then let's move the x-axis down to where I just said we wanted to have the origin. So if I do that, that certainly isn't going to change anything going on in the x direction, because I haven't changed the origin in the x direction. But for the y equations, these guys, we now have to sort of rethink what those are. So let's just get rid of those and think now what goes on for the y situation. Since the origin is down here, there's now an initial y position. In fact, it's that distance h that I keep drawing in here. And then also the component of the velocity is downwards, and that's now a negative value. And the acceleration due to gravity, of course, is downwards, and that's going to be negative as well. So now things look a little different. We've got the minus v0y times t, and then also minus 1/2 ag times t squared. But at the same time, well, let's go through. The velocity then also has a minus sign in it because the acceleration is downwards, and that's in the negative direction. Okay. So the other change, of course, is that at t is equal to this t final, the object in the vertical direction has just come down and it's hit the ground, so the final position is just equal to 0. So we can say when we plug in that value of t final that we should get 0. So what does that mean? If you take this equation now for y of t and you plug in t final, there it is in terms of symbols. What do we need to do? We're looking for h, so we just need to move these guys over to the other side where it's 0 over here. So if you do that and then turn it around, you get h is equal to that expression, which if you go back and look, that's exactly the same thing we had in the previous case. So when you plug in the various numbers, you just get that same 893 meters. So it's a reminder that it doesn't really matter what you do in terms of a coordinate system. You may have results that look fairly different from somebody else because you made one choice and they made a different one. but the answers you're going to get will be the same no matter what. All right, that gets us through the solution to this problem.